What's up, apes? And welcome to another episode of AP Environmental Science Non-Renewable Energy and Resources. So in non-renewable energy, in this section, we're going to talk about patterns of energy use, fossil fuel resources, and nuclear energy resources. In patterns of energy use, be able to describe the use of non-renewable energy in the world and in the United States. Explain why different forms of energy are best suited for certain purposes, and understand the primary ways that electricity is generated in the United States. Non-renewable energy is used worldwide in the United States. Fossil fuels are fuels that are derived from biological material that became fossilized millions of years ago. And these fuels from this source provide most of the energy used in both developed and developed countries. The vast majority of fossil fuels we use, coal, oil, and natural gas, they come from deposits of organic matter that were formed 50 million to 350 million years ago. As we saw in a previous section, organisms, they die, decomposers break down most of their dead biomass aerobically, and it quickly re-enters into the food web. However, in an anaerobic environment, like a swamp or a river or a delta or the ocean floor, for example, a large amount of detritus may build up very quickly. And under these conditions, decomposers cannot break down all of that detritus. As the material is buried under layers and layers of sediment and is exposed to heat and pressure, the organic compounds within there are chemically transformed into a high energy solid, liquid, and a gaseous component. And these are easily combusted. Because fossil fuels cannot be replenished once we use them all up, it is known as a non-renewable energy resource. Nuclear fuel, which is derived from radioactive material that gives off energy, is another major source of a non-renewable energy on which we depend upon. The supplies of this energy are what we call finite, which means they're going to run out. Every country in the world uses energy at different rates and relies on different energy resources. Factors that determine the rate at which energy is used include the resources that are available and affordable. In the past few decades, people have also begun to consider environmental impacts to make some of their energy use decisions. So let's talk quantities. To talk about quantities of energy used, it's helpful to use specific measurements. So if you recall, the basic unit of energy is a joule. And so 1 gigajoule is a billion joules, or about as much energy is contained in 30 liters, 8 gallons of gasoline. So a billion gigajoules is what we call an exajoule, which that's 1 times 10 to the 9th gigajoules. So this pie chart shows the 2011 total world energy consumption, that it was approximately 550 exajoules per year. This number amounts to roughly 75 gigajoules per person per year. And that includes oil, coal, and natural gas. Those are the 3 largest energy sources. Peat, which is a precursor to coal, is sometimes combined with other coal material, and that usually is available in the developing world. The energy is not evenly distributed throughout the world. So here we have the uneven energy distribution. The United States was 325 gigajoules per person per year. That's almost 5 times greater than the world average. In fact, although 20% of the world's population lives in developed countries, those people use 70% of the world's energy each year. So also note that some countries, shown here like China, they have the greatest total energy consumption, whereas Canada has the greatest per capita energy consumption. And that leaves Tanzania has the lowest annual energy consumption of the countries that are shown in this diagram. And an annual per capita energy consumption in Tanzania is less than 3 gigajoules per person per year. Now, there's a huge variety of reasons for these patterns that we see in developed countries and in urban areas of some of these developing countries. Individuals are likely to use fossil fuels like coal, oil, and natural gas, either where it's directly or indirectly. People living in rural areas of these developing countries primarily still use fuels like wood, charcoal, and even animal waste. It's these differences that lead us to distinguish between commercial and subsistence energy sources. Commercial energy sources are those that are bought and sold, like coal, oil, and natural gas. Although sometimes wood and charcoal and animal waste can even be bought and sold commercially. Subsistence energy are those gathered by individuals for like their own their own immediate needs and use. And that includes things like straws, sticks, and animal waste too. So there's a much greater use of subsistence energy sources in the developing world, especially in rural areas. So changes in energy demand generally reflect the energy demand increase. Societies change the types of fuels they use, and today we even see the same patterns of changing energy in developing countries that have been observed historically in the United States. For example, right now more people own automobiles than ever, and so the demand for gasoline and diesel fuel is high. As industries developed and factories are built, demand for electricity and nuclear fuel increases. And although worldwide energy use kind of varies considerably, the U.S. is a particularly large energy consumer. This diagram shows the history of energy use in the United States. Wood was the predominant energy source until about 1875, when coal came into a wider use. Starting in the early 1900s, oil and natural gas joined coal as like the primary source of energy. But by 1950, electricity generated by nuclear power became part of the mix, and hydroelectricity became more prominent as well. In the 1970s, we saw a decline of oil and the use of coal. And these changes were a result of a political, economic, and environmental factors that will continue to shape energy usage in our future, and we will learn about later. Today, though, the three resources that supply the majority of the energy used in the United States, in order of importance, are oil, natural gas, and coal. The recent increase in the consumption of natural gas is evident. You can see here in this figure that results of its increase in availability and decrease in its price due to this process called hydraulic fracturing or fracking. Energy use in the United States today is a result of inputs and outputs of an enormous system, and the boundaries of that system are not only political, but they're also technological and physical. Let me give you an example. Oil inputs enter the U.S. economies and the U.S. energy system from both like a domestic production and an import from another country. Hydroelectric energy comes from water that flows within the physical boundaries of the country. And well, as from neighboring Canada, but it's not an energy input until we move it technically into a technological system like a hydraulic dam. One major output of the system is work, the energy used for transportation, residential, commercial, and industrial. The other major output is waste, like heat and carbon dioxide, and all these other pollutants that are released as energy is converted and the entropy of the system increases. You can see in these graphs that U.S. energy consumption in 2012 was approximately 1 times 10 to the 18th joules per year. And the energy mix in the United States consumption is 82% fossil fuels, 8% nuclear fuel, and 10% renewable energy sources. So the United States produces 85% of the energy that it needs, while the remainder, like 15%, comes from other countries, primarily in the form of petroleum import. And the percentages of energy imports have been decreasing as domestic production of natural gas and oil increase. And so these trends are expected to continue. Industry uses more energy, followed by transportation being second. So I mentioned this earlier, that different energy forms are best suited for specific purposes. The best form of energy to use depends upon the particular purpose in which you need it. For example, transportation, we prefer gasoline or diesel fuel. Liquid energy sources that are relatively compact, meaning that they have a high energy to mass ratio. Imagine running your car on coal or firewood. I mean, to travel the same distance of a conventional car on a tank of gasoline, we would have to carry around much larger volume of material to make that work. So gasoline is the current fuel of choice for personal transportation. It gets you a lot farther in a much smaller volume. Energy to mass ratio is not only the only consideration, when it comes to fuel choice. A wood or coal fire starts relatively slow. If you use it in an automobile, you would not accelerate very quickly. Gasoline and diesel are also fuels ideal for vehicles because they can provide energy really quickly, and they can be shut off very quickly. Unfortunately, compared to other energy sources like natural gas or hydroelectricity, gasoline produces large amounts of pollution in the air. Even per joule of energy is released is much higher. In addition to that, unlike coal or wood, gasoline requires a good deal of refining and a chemical processing in order to be produced. So there are many factors to consider when determining the most suitable energy source for a particular application. We can actually calculate this. Although all conventional non-renewable energy sources have environmental impacts, to understand energy efficiency can help us make a better energy decision if we use some sort of math. So energy efficiency refers to the efficiency of the process we use to obtain the fuel and the efficiency of the process that converts it into work as needed. Every energy source from coal to oil to wind requires an expenditure. The most direct way to account for energy required is to produce a fuel or an energy source is by calculating the energy return on energy investment, what we call EROEI. The amount of energy we get out of an energy source for every unit of energy expended on its own production. So the EROEI is calculated as follows. Energy obtained from the fuel divided by the energy invested to obtain the fuel. So for example, in order to obtain 100 joules of coal from a surface coal mine, 5 joules of energy is expended. Therefore, 100 joules of EROEI equals 100 joules divided by 5 joules, and I get 20. As you might expect, a larger value for EROI suggests that a more efficient and more desirable process. So, we can talk about that. There's lots of movies on that following this unit. This diagram outlines the process of energy use from extraction to a resource to electricity generation and disposal of waste products from a power plant. The red arrows indicate that there are many opportunities for energy loss, each of which reduces energy efficiency. You may recall that the efficiency of converting coal into electricity is about 35%. We've discussed that earlier. In other words, about 2/3 of the energy that enters a coal-burning electricity-generated power plant ends up as waste heat or other undesirable outputs. And if we include the energy used to extract the coal, as well as the energy used to build the coal extraction machinery, construct the power plant, and remove or dispose of the waste and the materials from the power plant, the efficiency process would be like even lower. And we'll discuss that in later detail as well.